Hello, this is going to be one of those longer video about rotational motion, as I'm going to talk both about kinematics and dynamics in rotational motion. So first of all, for kinematics, there is angular displacement, which is also noted as theta, in which angular displacement is technically the same thing as angle. So for example, when theta equals to 2 pi, this is when an object went through a one full cycle. So for example, if there is a rod, and if this went around one circle, then we can claim that the angular displacement of this rod equals to 2 pi. Another example would be when theta equals to pi instead of 2 pi, this would be half a cycle. So a rod that is rotated by an angular displacement of pi only went through like a half a cycle of this rotational motion. So therefore, the distance traveled by an object equals to r times theta, where r is the radius. So for example, a rod with radius r that traveled, let's say, an angular displacement of 2/3 of a pi, then the total distance that is traveled, that is traced by this arc length, would equal to r times 2/3 of pi. There is also angular velocity, which is denoted as omega, and definition of this would be change in theta over change in time, and in terms of derivative, this would be d theta over dt. One thing to note is that angular velocity omega is different from frequency, in which the unit of angular velocity is radians per second, while for frequencies it is cycle per second. So for example, let's say it took this rod 3 seconds for it to travel angular displacement of 2 pi. Then omega equals to 2 pi over 3 seconds, which would be 2/3 of a pi radians per second. Meanwhile, frequency would just be 1 cycle per 3 seconds, which would be 1/3 times second inverse. So therefore, one generalization can be that omega equals to 2 pi times frequency. This is like a main difference between angular velocity and frequency. And similarly, just how distance equal to r times theta, velocity is also equal to r times omega. This is another fact to note. And for, in this case, r times omega, this would be the perpendicular velocity. What I mean by that is, if an object is separated by distance r and is rotating at angular velocity of omega, then the perpendicular component of the velocity would be r omega. But this does not tell anything about the parallel component of the object's velocity. There is also angular acceleration. And angular acceleration is denoted as alpha, and this is similarly defined as d omega dt, or d2 theta over dt squared, or it's another word for second time derivative of angular displacement. And obviously, just how velocity equals to r times omega, the acceleration along the perpendicular direction equals to r times alpha. Now, in terms of equations of motion, there is similarity between linear motion or translational motion versus rotational. So for constant velocity, in normal kinematics, it was x equals to vt, where x is displacement and v is velocity, t is time. Similarly, in rotational motion, if velocity is constant, then theta, which is the angular displacement, equals to omega times t. For constant acceleration, the four equations of motion were v final equals to v initial plus at. Second one equals to displacement equals to the initial velocity plus final velocity over 2 times t. Third one is x equals to v initial t plus 1/2 at squared. And the fourth one equals to x equals to v final squared minus v initial squared over 2a. Similarly, we just replaced all the linear terms or the translational terms into rotational terms. So the first equation would be omega final equals to omega initial plus alpha t. Second would be theta equals to omega final plus omega initial over 2 times t. Third equation would be theta equals to omega initial t plus 1/2 alpha t squared. And the fourth equation would be theta equals to omega final squared minus omega initial squared over 2 alpha. So on the F equals MA exam, there aren't that many questions asking specifically for rotational kinematics, but it is really important to at least know what these are. Now let's move on to rotational dynamics. There is a term called torque, in which this is parallel to force in translational motion. And torque, which is a vector quantity denoted as tau, is equal to R cross producted with force. And if you forgot what the definition of cross product meant, this means the magnitude of R times magnitude of the force times sine theta, where theta is the angle between the displacement R and the force. So for example, let's say an object is separated by distance R and is exerted by a force F0 with angle theta to it. Then the torque with respect to, let's say this point is P, the torque with respect to point P equals to R cross F. In this case, it would be R times F0 times sine theta. And the direction of this torque vector is, although you can use the right hand rule for the cross product, how I remember is, since force is going to rotate this object along this way, then I'm going to use my right hand to curl it along that direction. And since my thumb is pointing into the page, the direction of the torque vector would be pointing inside the page. And conversely, if the force was directed upon this way, then the direction of the torque would be pointing outside of the page. Now let's say there is an object with radius r, and there is a constant force with magnitude F0 that is applied perpendicular to this radius and is separated by a distance r from the center of mass. Then the question is, how is torque, in this case equal to r times F0, is related to the angular displacement theta? Now torque can be represented as sum of Ri times delta m times Ai. Now what this means is that I in this case is index, and for every quote-unquote index, for every small mass of this object, they're going to accelerate perpendicularly from the radius Ri at a magnitude Ai, because as this force is pulling this object, this is going to rotate, and therefore every part of this small mass is going to accelerate at a different direction with different magnitude of acceleration. Now, since I said the perpendicular acceleration is equal to r times alpha, in this case, this equal to the sum of mi, or delta m, times ri squared times alpha. And using calculus, by putting this delta m by infinitesimal mass dm, this is going to be equal to the integral of r squared dm times alpha. And this quantity of the integral of r squared dm is going to be called the moment of inertia I times alpha. Now, one thing to note is that Newton's law was F equals to ma. Similarly, in rotational motion, torque equals to I alpha, in which a moment of inertia is parallel to mass in translational motion. So let's calculate the moment of inertia for a certain situation. Let's say a point mass of mass m is separated by a distance r. Then the moment of inertia, which equals to r squared dm, is just simply mr squared, because there is only this one point mass here separated by distance r. So therefore, the moment of inertia is just simply mr squared. Similarly, if there is a ring with mass m and has radius r, inertia, which equals to r squared, which equals the sum of r squared dm, is also mr squared. Because all of these small masses within the ring is separated by distance r, the inertia similar to a point mass is also going to have inertia of mr squared. Now, for example, let's say there is a circular object, circular disk with mass m and radius big R. Then the inertia equals to the integral of r squared dm. And from u substitution, or similar to u substitution, this equals to r squared times dm dr times dr. Now solving for dm dr, if I write m as a function of r, what I mean is that if there is, for a distance r, the mass of this inside circle equals to big M over pi big R squared times pi r squared, since this term equals to the mass density and this equals to the area. Canceling out the pi, this equals M over big R squared times R squared. Now it is very important to differentiate this big R, which is the maximum radius, and this R, which is just like a variable term. Differentiating this, dm dr equals to 2 big M over R squared times R, since this is a quadratic term. So therefore, plugging this into the integral, inertia equals to integral of R squared times 2 times M over R, big R squared R dr. Solving this and putting this constant out, this equals to 2m over R squared times integral of R cubed dr, in which this is 2m over R squared times 1/4 R to the fourth. And the bound of this integral is going to be 0 to big R, because we started at the center all the way up to the end with radius equal to big R. And obviously, evaluating this integral, this is going to be 2m over R squared times 1/4 R fourth, in which this would be 1/2 mr squared. Now, so therefore, if there is a circular disk with radius r and a constant force of F naught that is perpendicular to the radius, torque equals to R times F naught is also equal to I times alpha. In this case, inertia equals to 1/2 mr squared. So therefore, angular acceleration equals to R F naught divided by 1/2 mr squared, which equals to 2 F naught over mr. Now I can use this again to solve theta of t, in which theta of t would equal to omega initial angular velocity times time plus 1/2 alpha t squared. And I can just simply plug this value in with a given initial angular velocity. Now, since it is very tedious to calculate the inertia of these objects, there are some list of inertia that is useful for you to memorize. So for a point mass or a ring with mass m and radius r, the inertia equals to mr squared. And for a circle, the inertia equals to 1/2 mr squared, in which m is the mass and r is the radius of the circle. For a rod of mass m and length l, the inertia at the center of mass, inertia at the midpoint of this rod, equals to 1/12 ml squared. And obviously the mass length density have to be uniform. Also, the inertia at the end of this rod, inertia at the end point of this rod, equals to 1/3 times ml squared. For spheres, for a hollow sphere, the inertia equals to 2/3 mr squared, in which m is the mass and r is the radius of this hollow sphere. And for just a normal sphere that is not hollow, the inertia equals to 2/5 times mr squared. Now, for these two, it's kind of hard to memorize, and the way I memorize is that the denominator, the numerator is always going to be 2, but since for hollow sphere, more masses are located towards the end, it's going to have a larger moment of inertia. Therefore, it is going to have a smaller denominator than the just the normal sphere. Now, a rotating object has kinetic energy, in which rotational kinetic energy, in which I'm going to denote it as Ke rotational, is equal to the integral of torque with respect to theta. And this is similar to how the kinetic energy in translational motion equals to the integral of f dx, where we're integrating force or rotational force with displacement, with angular displacement. Now, similar to the logic behind integral of f dx, integral of torque with respect to theta equals to inertia times alpha times theta. And alpha from, theta from the kinematics equation, this equals to alpha times, this equals I times alpha times final omega final squared minus omega initial squared divided by 2 alpha. Dividing the alpha, this just equals to 1/2 I omega final squared minus 1/2 I omega initial squared. So therefore, I can define kinetic energy of rotating object as 1/2 I omega squared. Now, note that this is also parallel to the translational kinetic energy equal to 1/2 mv squared, where again, mass is parallel to inertia and velocity is parallel to angular velocity. So therefore, if an object is rotating at angular speed omega and is moving linearly with speed v, then the total kinetic energy equals to the translational kinetic energy plus the rotational kinetic energy. In this case, this equals to 1/2 mv squared plus 1/2 I omega squared. Now there is a theorem called parallel axis theorem, which is useful for calculating inertias of an object at a point that is not at the center of mass. So for a generic object with this shape, and let's say this is the center of mass, this has the inertia center of mass of ICM. And with respect to point P, which is separated by distance d, this is rotating at angular speed omega. Then the rotational motion along P, I'm just going to call it rotation along P, is equal to rotation along center of mass plus translational motion with velocity vcm. What I mean by that is this rotating at point P equals to this object rotating along the center of mass plus moving translationally with velocity v center of mass. And therefore, using the conservation of energy equation, 1/2 IP omega squared equals to 1/2 ICM omega squared plus 1/2 mv center of mass squared. Now, since v center of mass is what is going to be perpendicular with respect to d, v center of mass is going to be d times omega. Therefore, plugging this back in, the equation is going to be 1/2 IP omega squared equals to 1/2 ICM omega squared plus 1/2 md squared omega squared. And canceling out the 1/2 omega squared term, I get IP equals to ICM plus md squared. So let's look at some examples of this parallel axis theorem. So let's consider this rod of mass m with length L. Then I center of mass, I said equals to 1/12 ml squared previously. Now evaluating the inertia equals to integral of r squared dm dr with integration bound from 0 to L over 2. Now this integration bound is from 0 to L over 2 because we're starting from center of mass to the endpoint, which distance equals to L over 2. And we have to multiply this by 2 because this integral is inertia of half of this rod, so therefore we have to add these two in order to get the inertia of this full rod. dm dr is simple. Since the rod has uniform mass density, this is just simply m over L. So therefore, evaluating the integral, this equals to 2m over L times the integral of r squared dr, which is 2m over L times 1/3 times r cubed from 0 to L over 2. And thus, further evaluating this equals to 2m over L times 1/3 times L cubed over 8. And canceling out some terms, I get 1/12 ml squared. Now, the inertia of the same rod with mass m and length L at the end point this time, the inertia at the end point equals to integral of r squared dm dr from integrating from 0 to L. This time we're not multiplying by 2 because previously when we're evaluating the inertia at the center of mass, there were two masses from starting at distance 0 to all the way over L over 2. But this time there's only one chunk of mass that we need to evaluate. And from the same logic as previously, dm dr is simply m over L since the mass length density is uniform. Therefore, evaluating this integral, this is simply 1/3 r cubed times m over L from the bound 0 to L, in which this is 1/3 L cubed times m over L, which becomes 1/3 ml squared. Now let's check if this aligns with the parallel axis theorem. Parallel axis theorem claims that I at the endpoint should equal to I center of mass plus 1/2 plus md squared, where in this case d equals to L over 2 and I center of mass equals 1/12 ml squared. So therefore, I at the endpoint should equals to 1/12 ml squared plus m L over 2 squared, in which this equals to 1/12 ml squared plus 1/4 ml squared, and 1/12 plus 1/4, this equals to 1/3 ml squared, in which this aligns with the value of inertia that we got from the integral. Similar to parallel axis theorem, there is perpendicular axis theorem, in which this only applies for flat objects. So for example, let's say there is a flat object that looks like this. Then the inertia along the z-axis, what I mean is if this axis is x and if this axis is y and z-axis is pointing out of the page like this, the inertia of this object of rotating along the z-axis, which means rotating along that way, is equal to inertia along the x direction plus inertia along the y direction. Now what this means is that inertia along the z direction from the definition of inertia equals to sum of mi ri squared, where for every index this equals to ri. And from Pythagorean theorem, this ri squared equals to xi squared plus yi squared, where xi is the distance of the x direction and yi is the distance of the y direction. And separating these two terms, this equals to the sum of mi xi squared plus sum of mi yi squared. Now the sum of mi xi squared, this equals to the inertia along the y-axis, because if I rotate this flat object along the y direction like this, so it would go along this way, then the inertia equals the sum of mi times the distance from the y-axis of that small mass, in this case equals to xi. And similarly, the sum of mi yi squared equals to ix, in which this equals the inertia of this object that is rotated along the x direction, so it would go along that way. So therefore, iz would equal to ix plus iy. So an example of using perpendicular axis theorem is getting an inertia of the circular disk that is rotated along this direction. So what I mean is that for a circle that is rotating on parallel to the surface, so if this circle is rotated this way, then the inertia equals to 1/2 mr squared. Then if I set this perpendicular axis as z, then iz equals to 1/2 mr squared. And from the perpendicular axis theorem, this equals to ix plus iy, where ix is the inertia that is rotated along the x-axis, and iy equals to moment of inertia that is rotated along the y-axis. Now from symmetry, the ix and iy are the same, because if this circle, let's say if this is like a shape of a circle, if the circle is rotated this way and if the circle is rotated that way, since the shape and the orientation of this circle is the same both for x direction and the y direction, ix is actually the same value as iy. Therefore, iz equals to 2 times ix, and conversely, ix is 1/2 of iz, which would be 1/4 mr squared. So for example, for a circle like this, if a force of constant magnitude F naught is applied perpendicular with respect to the radius, then torque, which equals to r times F naught, equals to iz alpha, which would be 1/2 mr squared. This would be iz because the direction of rotation is along the z direction that is located perpendicular to the surface of the circle. However, if the force is applied this way, where it is perpendicular to the surface and it is also perpendicular to the radius like that, then torque would be also equal to r times f naught, because the cross product between the radius and the force would just be r f naught. But in this case, this would be ix alpha, because the axis of rotation is along the x direction. So like the circle would be rotating this way instead of that way. So therefore, in this case, this would be 1/4 mr squared alpha, in which comparing this alpha to that alpha in this value would be greater because inertia is smaller. So I've prepared several questions from the F equals ma exam relating to rotational motion, and the first one's from year 2016, question 18. So in this problem, an object is spinning, and if I draw the angular velocity omega with respect to time, initially it says the object is accelerating at certain angular velocity up to pi over 15 radians per second. And then it is going to continue at this constant speed and then decelerate at the same angular acceleration. And it says the angular acceleration equals to pi over 75 radian per second squared. So when it's decelerating here, it's going to be negative pi over 75 radians per second squared. So if I calculate this time here, since it is at constant acceleration, omega final equals to omega initial plus alpha t. And since the initial angular speed is 0, this is simply alpha t. Therefore, the time it took for the object to accelerate equals to omega over alpha, in which this is pi over 15 radians per second over pi over 75 radian per second squared, in which this becomes 5 seconds. So it took 5 seconds for the object to accelerate, and then took another 5 seconds for it to decelerate. If I call this time of the object spinning at constant velocity time big T, then theta in this case equals to 1/2 alpha t squared, in which this is the constant acceleration motion, plus omega big T, in which that is the constant velocity motion, and plus 1/2 alpha t squared equals to alpha t squared plus omega big T. And substituting each value for alpha, t, and omega, this becomes pi over 75 radians per second squared times 5 seconds squared plus pi over 15 radians per second times big T, in which it says the spinning object went through 3 cycles, in which converting it to angular displacement, this equals to 6 pi. So calculating this value, this equals to pi over 75 times 25 plus pi over 15 times t equals to 6 pi. Canceling off the pi, this value is 1/3, and this is pi over 15, that is 6. So therefore, t over 15 equals to 6 minus 1/3, which is 17 over 3. And multiplying each side by 15, t equals to 17 over 3 times 15, which becomes 85. Now, since this t is the time for the object to move at constant velocity, I need to add these 2 times, which in total add up to 10 seconds. Therefore, t total equals to t plus 2 small t, which is 85 seconds, plus 2 times 5 seconds equal to 95 seconds. So the next question is from the same year, question 24, and which is about inertia. It is given that for a equilateral triangle of mass m and side length a, the inertia along one of its side equals to 1/8 ma squared. And the question is asking, what is the inertia of the hexagon with side a mass m that is rotated along this axis? Now, in this question, I'm first going to split this hexagon up to 6 pieces, so it looks like 6 different triangles, in which I've noticed that the inertia of this hexagon equals to 4 times the inertia of this triangle along this side, plus 2 times the inertia of the triangle that is rotated along its vertex. And So since I know the inertia of the triangle that is spun along its side, I only need to calculate the inertia that is rotated along its vertex. And I'm going to use parallel axis theorem in order for it to do so. So for this triangle, the center of mass is actually located at the 1/3 of its height. And since the side equals to a, the height equals the square root of 3 over 2a. So therefore, this distance here is 1/3 times this value, which is square root of 3 over 6 times a. So therefore, using parallel axis theorem, 1/8 of ma squared equals to I center of mass plus md squared, which d in this case equals the square root of over 6a. So therefore, this is m times square root of 3 over 6a squared, which is I center of mass plus 3 over 36 ma squared. Solving for I center of mass equals to 1/8 minus 3 over 36 ma squared, and since this equals to 1/12, this value becomes 1 over 24 ma squared. Now because I got the I center of mass, I can use this again and the parallel axis theorem to get the moment of inertia at the vertex. In this case, the distance here is square root of 3 over 3a, since this should be the double of square root of 3 divided by 6a. So therefore, I vertex equals to I center of mass plus m square root of 3 over 3a squared, in which this is 1 over 24 ma squared plus m times 3 over 9a squared, which is 1 over 24 plus 1/3 ma squared, which equals to 3 over 8 ma squared. So the inertia of this hexagon along this axis equal to 4 times the inertia along the side plus 2 times the inertia along the vertex, in which this is given as 1/8 ma squared, and this we just calculated equals to 3/8 ma squared. Now remember that each of this triangle has mass of 1/6 m. So therefore, the inertia along the side equals to 1/8 times 1/6 m times a squared, which equals 1 over 48 ma squared, and the inertia along the vertex equals to 3/8 times 1/6 ma squared, which equals to 1 over 16 ma squared. So therefore, plugging in these values here, this becomes 4 times 1 over 48 ma squared plus 2 times 1 over 16 ma squared, which this becomes 1 over 12, that becomes 1 over 8, and if I add 1/12 with 1/8, this becomes 5 over 24 ma squared, in which this value, if I look at the answer choice, equals to B. So the next question from 2017 F equals MA, question number 6. So in this problem, the following system is under static equilibrium. And in order for this to be at static equilibrium, the net torque must equal to 0. And along this axis, since this 200 gram and 500 gram is exerting opposing torque with 400 grams and m3, the torque from these two masses must equal to torque from these two masses. So therefore, 400 grams times 10 meter per second squared times 0.4 meters, note that this is force times the displacement or the distance from the axis of rotation, plus m3 times 10 meter per second squared times 0.2 meters should equal to 200 grams times 10 meter per second squared times 0.5 meter plus 500 grams times 10 meter per second squared times 0.4 meters. Now here, the gravitational acceleration, the 10 meter per second, can be all cancelled off, in which if I solve for m3, I get m3 equals to 200 grams times 0.5 meter plus 500 grams times 0.4 meters minus 400 grams times 0.4 meters divided by 0.2 meters. In which, solving for this, I get 100 grams times meter plus 200 grams times meter minus 160 gram times meter divided by 0.2 meters, in which this, adding these two, this is 300, subtracting these, this is 140, and 140 divided by 0.2 equals to 700 grams. So therefore M3 must equal to 700 grams in order for this system to be at static equilibrium. So therefore, looking at the answer, E should be the correct answer choice. The next question from the same year, question 14. It is asking, among these four objects with mass m and r, which would have the largest acceleration down the incline when this is placed on an inclined plane? So the system looks like this. There is an inclined plane of angle theta, and there is an object with mass m and radius r. Then the torque is applied by the force of gravity, mg, in which torque equals to r times mg times sine theta, in which this is also equal to inertia times alpha. Since this is all constant for all four options, because all of them has the same mass and same radius, the angular acceleration, which is proportional to the linear, so the linear acceleration, which is proportional to the angular acceleration, is proportional to the inverse of inertia. So therefore, inertia must be small in order to have a large acceleration. So for answer choice A, it says a uniform solid sphere, in which uniform solid sphere has inertia of 2/5 mr squared. For B, it is a uniform solid disk in which inertia equals to 1/2 mr squared. For C, it says it's a hollow spherical shell in which inertia equals to 2/3 mr squared. And for D, a hoop has inertia of mr squared. Since the solid sphere has the smallest inertia, answer A is the correct answer. So the next question is question 15 from the same year, which is really similar to question 14. In this problem, this is asking, if an object went down a height of h, then which of the following objects among the answer choices is going to have the greatest speed? Since energy is conserved, initial potential energy is going to be the final total kinetic energy, which this equals to the rotational kinetic energy plus the translational kinetic energy. So therefore, plugging in the value, mgh must equal to 1/2 I omega squared plus 1/2 mv squared. And assuming that I is in the form of beta mr squared, this is 1/2 times beta mr squared omega squared plus 1/2 mv squared. Since this object is rolling down the incline, v equals to r omega. And if I plug this value here, mgh equals to 1/2 beta mv squared plus 1/2 mv squared. Canceling off the m, I get v squared 1/2 v squared equals gh over 1 plus beta, in which if beta is small, then v squared is going to get larger, which means v is going to be larger. So therefore, I just need to pick an object that has the largest value of b. However, if I look at all of these answer choices, I've noticed that A is a sphere, B is a sphere, C is a sphere, and D is a sphere, in which inertia is going to be some form of 2/5 mr squared, which means beta is going to be constant for 2/5. So therefore, all these four objects is going to have the same velocity, and therefore E is going to be the answer. The next question is from 2018A, question 8. So in this question, there is a large hoop that is stationary with radius r, and there is a smaller hoop of radius small r that is rolling around this hoop. And the time it takes for this hoop to go around one cycle is big T. And it is asking, what is the speed of this end of this hoop? Now, the distance that is traveled by the center of mass of this small hoop which if I trace the path, it's going to look like this. The distance is going to be 2 pi times big R minus R, because this radius here, the radius of this traced path, equals to big R minus R. Therefore, the distance equal to circumference of this circle. So therefore, V center of mass, which equals the distance divided by t, equals to 2 pi big R minus R over t. Now, since this hoop is rolling, I can claim that V equals to R omega. And at the opposite end, the R here equals to 2R, in which this equals to 2R times omega, which, since R omega equals V center of mass, this is going to be 2 times V center of mass. Therefore, V at the end is going to be 4 pi times big R minus R over t. And looking at the answer, it seems like answer choice D matches to my calculation. Next question is question 9. And in this problem, there is a rod of mass m, which is pulled up by a force with magnitude F. And there is also a normal force that is applied from this surface upward, while there is the weight, the force of gravity exerted downward. And the question is asking, what is the range of this normal force? So I can apply two equations. One is F equals ma, or the F net equals ma, and the second one is torque net equals to I alpha. So using Newton's law first, the net force equals to force at the F plus N minus mg, which equals to ma. For the torque, the angular acceleration here is equal to a over L over 2, because this center of mass is going to accelerate because the acceleration from the net force is the acceleration of the center of mass. And since this point is stationary as this is attached to a surface, the angular acceleration is simply a over the distance, in which this distance equals L over 2. So therefore, angular acceleration is 2a over L. So the net torque, the torque along the center of mass, is going to be F times L over 2 minus N times L over 2. And this equals to I alpha, in which this is 1/12 ml squared times 2a over L. Now solving this equation, I get F minus N equals to 2 times 2 divided by 12, 1 over 12 ma, in which this is 1/3 ma. So with combination of this equation, I get F minus N equals to 1/3 ma, and F plus N equals to mg plus ma. And if I subtract this equation, then I get negative 2n equals to minus mg minus 2/3 ma, in which n equals to 1/2 mg plus 1/3 ma. Now, therefore, since acceleration is always going to be positive because it says this rod is going to be lifted, the minimum normal force is going to be 1/2 mg, because this is when acceleration equals to 0. So therefore, n must be greater than mg over 2. And looking at the answer choice, B is the only answer choice that satisfies the condition of where normal force is greater than mg over 2.